So this is the amplitude modulation DSB AM transmitter kit. This section over here is the audio oscillator, wherein the amplitude can be varied from 0 to 2 peak to peak volts, and frequency in the human audible range from 300 to 3.4 kilohertz. The signal is fed from this stage and it goes into the modulator section, wherein you can change the balance or the depth of modulation with this knob. And on this side, the carrier which is generated at 1 megahertz, it can be 100 millivolts peak to peak, which is generated using a crystal oscillator, and that is fed as a second input to the modulator. And the modulator output, which is again measured, produces the amplitude modulated signal. So these are the waveforms. The above blue waveform is of the audio signal, which is our message. It has a frequency of almost, as you can see, 3.35 kilohertz, and with a peak to peak of 2.64 volts. We can and the below waveform is the modulated AM signal waveform, which has a frequency of around 1 megahertz, which is the carrier frequency, and has a peak to peak of 1.3432 almost volts. And we can vary the amplitude of our message signal. The frequency of our message signal has been increased and decreased, and we can see that the modulated signal also varies accordingly. We can also increase or decrease the amplitude of our message signal, can decrease the amplitude, and we can see the modulated signal also copies that with good fidelity. Also, we can change the balance or the modulation depth with the knob provided in the modulator, and accordingly the modulation index also changes. So it can be either modulation index greater than 1, or between 0 and 1, or it can be less than 1 as well, right? So this is distorted signal, right? We don't transmit it at this level. We would ideally want modulation index to be greater than 0. Okay, so after that, the output amplifier output from the antenna, because we'll be transmitting the signal wirelessly, would be noted, and that should be the AM signal, but in an amplified mode. In order to check whether the antenna is transmitting, we can just hold the antenna and we'll see the loading in the signal happening. So that would confirm that our antenna is transmitting the signal, and the signal being transmitted is almost 1.3 kilohertz. In order to see whether we are receiving the correct signal, which is being transmitted by the transmitter into the receiver, we can check the signal at the transmitter through the inbuilt speaker, and this is the frequency right now, which is 1.3 kilohertz, and we can change the frequency in order to confirm, right? This is, I think, a shorter frequency, longer wavelength, and this is the shorter wavelength. So once that is confirmed, we'll move on to the receiver section. Okay, on the receiving section, on the receiver, the receiving antenna actually receives a signal, and that is actually fed first to the RF amplifier stage, whose gain we have put to the maximum. That is actually that would be centered at our carrier frequency, which is 1 megahertz in this case, and it needs to be tuned, because we can change the tuning, because we can change the tuning frequency within the range, and that would essentially, as is shown, change the local oscillator, which is Local oscillator is 455 kilohertz in this case, which is the intermediate frequency above the center of the RF amplifier, which we tune of the right. So once that is tuned, which is around in this 0 to 100 scale, around 55 58, right, then our RF amplifier is detecting the amplitude modulated signal, but that would be it would amplify the frequencies which are more near the 1 megahertz range. So after that it is transmitted, it is given to the mixer stage, wherein the local oscillator is mixed with it in order to get the intermediate frequency IF, and then that is set to the 2 IF stages, which amplify our signal because it's very weak in millivolts, even microvolts. And after 2 stages of IF amplification, which obviously are centered at the 455 kilohertz, the signal is fed in this case to the diode detector of DSB, which is actually an envelope detector, a diode in series and capacitance and resistance in parallel. And in order to we have activated the automatic gain control circuit as a feedback, as you can see in this case, which actually changes the gain of this first IF amplifier, which would compensate for the certain increases in the input voltage level if our signal if our transmitting signal is too close. So that would be the functionality which we are activating in this case. After the diode detector, the output would be our message signal, which was sent in this case at 300 kilohertz, at 3 kilohertz almost, and that is fed to the audio amplifier. This gives a large gain to almost 10 volts, which would be sufficient for a speaker to function. And now let us increase the volume and see what we are receiving in this case. And this is the exact signal which we received, which we are receiving, which is 3 kilohertz, which we had sent our message signal. In order to confirm that, we can firstly do the tuning, right? And just as a super heterodyne radio receiver, our signal would be received at the appropriate frequency, which is 1 megahertz in this case. And here you see, this is the point how we tune it, the Ganj amplifier, in a super heterodyne receiver. And in order to confirm that whether it's our transmitted signal, we can change at the transmitting end the frequency, and this clearly actually changes the reception signal, which would confirm that this is the actual signal which is transmitted by our Scientech transmitter. Okay, now is the time to see the waveforms on the receiver's kit. At the top in the blue is the transmitted signal, which is of 1.6 kilohertz over the carrier of 1 megahertz, as you know. And the below waveform is the direct signal received by our antenna, which contains a lot of noise plus all the frequencies present in the environment. So the first job to do is remove the unwanted frequencies and just concentrate on our transmitted frequency, so which is 1 megahertz in this case. And this is the output of the RF amplifier, wherein you can see that the carrier has been detected because our RF amplifier is tuned to the correct frequency of the reception and is amplified a bit as well. As we can see, the peak to peak is 18 almost 16 millivolts of the received signal after RF amplification. Now the signal is needs to be further amplified, and the unwanted frequencies still need to be removed in the next stages. So now it is mixed with the local oscillator, and the output, as we can see, this is the local oscillator, which is 455 above. Automatically it is set 455 above the tuned frequency, which is in this case 1 megahertz plus 455 kilohertz, 1.45 megahertz. And the output of the mixer is this waveform, which is amplified a bit, but the unwanted frequencies have been removed from this considerably. Now is the time to see the output of the first IF amplifier stage. So this is its output, and as you can see, it is amplified by a huge amount. So we need to reduce the scope so that the waveform comes inside the received area of the CRO, and you can see that the peak to peak has now jumped to 65 millivolts. And remember, for this at the receiver we need to use a different probe which is called X10 probe, which does not load our very minute signal levels, and yet can detect the signal levels. Now the output of the second IF amplifier stage, that's here. You can see further amplification. Further you need to reduce the scope, and this now the peak to peak is 0.2 volts, which has been considerably increased. Now this output, as we know, goes to the diode detector. The output of the RC diode detector, this is the output of the diode detector, and as you can see, this contains our signal. This is our message signal plus the DC level plus the ripples, which need to be removed in the next stages. But for the diode detector, actually we can change the resistance of that's a variable resistance potentiometer in order to see the envelope detection process. Now as I change the potentiometer, if I increase the resistance, as you can see, this is at the highest resistance level, right? If I reduce it, right, so there you can see the change, right? So essentially it won't follow the signal because it would be there's a trade-off between the time constant, which actually changes because of this. So maybe you can increase the scope in order to say this is the change which I was talking about. If you reduce it, it won't follow the signal. If you increase it to the maximum, you can see it follows the signal, but still there are some excursions. Now these excursions could be removed by the audio amplifier, and now this is the output of the audio amplifier, which is a very high gain amplifier. The peak to peak, as I can increase the peak to peak, I have reduced it intentionally so that it comes in the scope, but two things are removed. One, the DC level, and the ripples are considerably removed. Also you can clearly see that the waveform, yellow output waveform of the audio amplifier is inverted. That's because it gives a phase shift of 180 degree to the input, to the output of the diode detector. And as we know that this is the signal, let me increase the this level, gain level, and this is the received signal, right? I'll increase it, and we can increase it to to a large extent. This is the highest increase, and you can see the peak to peak is almost 1.12 volts. Just there you go. The peak to peak is almost we can keep it to 1 volts, and that can be fed to the speaker. This is our transmitted message at the transmitted frequency, right? A further interesting thing to do with these kits would be if instead of our sinusoidal signal of that frequency, the 1 to 3 kilohertz, we can send the human voice, because that's from 300 to the 300 to 30 303 megahertz, 300 hertz to 3 kilohertz, which can be sent through this same receiver. So now what you can see on the scope is the blue or top line is the analog signal, which we are going to send, in this case human voice, and the received AM signal is given in blue, is given below in yellow. And let us now turn on the audio amplifier at our receiver and see what we receive. So I hope you can hear the sound which is received, because I'm not transmitting anything yet. Now I'll be transmitting my voice through the microphone and the transmitter. Hello, hello, hello. So as you can see, as I'm speaking, the signal message signal changes, and that actually changes the modulated wave as well. So that is how we transmit AM. And remember, this is the case of DSB, and carrier also has been transmitted, which is actually the type of modulation we do in the radio broadcast stations. AM, which we receive on our radio receivers, it should be a super heterodyne type receiver. We can also see the effect of the automatic gain conversion circuit, AGC circuit. If we increase the output amplifier at the transmitter, we'll see that slowly the received signal also increases, and this is the received signal in yellow, quite in fidelity with the transmitted signal. But as I increase the transmitter gain, after a certain threshold, the received signal reduces, because there is no automatic gain control in this case, which I've turned off. And if I increase the gain further, your received signal would be diminished to such an extent it would be distorted. But if you turn on the AGC circuit, automatic gain conversion, it actually looks at the gain at the input signal levels, and accordingly reduces the gain as required, right? So for AGC, it's a boon in that case. The selectivity of curve of this receiver can also be plotted. At the top is the received message, and in yellow and blue is the received modulated signal. If we right now it's tuned to the receiver frequency, that is which was transmitted at 1 megahertz. If we change or decrease or increase the frequency, obviously we can see the change in the amplitude. The amplitude of the received signal will reduce at the reduced frequency. So this is the reduced frequency, and as you can see that the signal is distorted. And again, if you slowly increase it to the resonance, which is 1 megahertz in this case, again the signal is retrieved. And if we increase the frequency, again the signal amplitude reduces. By that we can calculate the selectivity. Also, the fidelity of the receiver can be measured. If we look closely at the received signal waveform at the top, below one blue is the transmitted signal, and if we now increase the transmitted message frequency, and right now it is at the highest frequency, which is I think 4.5 kilohertz. Reduce it gradually, and you can see if we look keenly, the amplitude of the received signal slightly increases, and this is at the maximum right now, and I think the maximum is around 900 hertz. And as you reduce the frequency, again the amplitude reduces. Peak to peak it is I think 200 millivolts. So this will help us to plot the fidelity curve of the receiver. And if you look closely, the peak to peak goes from 206 millivolts, and right now it's gone down to 178 millivolts at high frequency, and at low frequency it again reduces. Now something interesting, if we turn off the transmitter and now our receiver is receiving the signals from the environment, we can essentially tune in to a local broadcasting station, which is 1116 DD Srinagar, using our tuner. So let us see that thing. I'm turning it on, right, and I have to tune directly to that frequency, that is 1116 kilohertz, which is AM. So you can see, just there you go. This is the DSB Srinagar, which we have received, because this is a DSB DSB signal which is being broadcast, which has a very high range of almost 40-50 kilometers, just like a radio, super intermittent receiver.